Good morning, class. Okay, everybody, please stand up. Let's start our day with a prayer. May I request Class Mayor to please lead the prayer for today? In the name of the Father, and to the Son, and to the Holy Spirit. Amen. Okay, thank you so much, Miss Mayor. Good morning once again, class. By the way, I'm Mylene G. Aguilar. You can call me Teacher May or Teacher Lynn, and I will be your teacher for today. Okay, Class Bidel, may I know who is the absent for today? Very good! There is no absent for today. I really appreciate it, class. So everybody is present. So before we continue our discussion, let me introduce first our classroom rules. First is, be quiet when the teacher is talking. Second, respect and listen to your classmates when they are sharing their ideas. Third, gadgets are not allowed during the discussion unless it's emergency. And the last one, raise your right hand if you want to questions or to answer. Am I clear, class? Last meeting, we discussed about the axioms of infinity and successor set. Now, who can tell me or who can differentiate the definition of axioms of infinity and successor set? Okay, yes? Thank you, very good. It seems you still remember our topic last meeting. Before we continue our lesson for today, we have first a group activity. But before that, let's have our group first by counting 1, 2, 3. Start here. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, and 3. Okay. Now, I want you to go to your group mates silently and form a small circle. Remember to choose a secretary and a leader, and the secretary will write all the group members' names in a 1/4 sheet of papers. Okay, class, our first activity is called Break the Code. So, here is the mechanics. I will give each group a bond paper and a pen. Then, when you finish breaking the code, write your answer in the bond paper, and the group leader will stick it on the board. The first group who finish and get the correct answer will get 15 points, the second is 13 points, and the third will get 10 points. So, are you ready? Okay, your time will start now. Good job, students! All of you get the correct answer. So, based on our activity, what would you think will be our topic for today? Anyone? Yes? Okay, very good. Our topic for today is all about Peanos axiom and recursion theorem. But before that, let's have first another activity. Your second activity is called Arrange Me. Everybody, please read the directions. So, this is the mechanics of your activity. You will work as a group, then I will give you 5 minutes to answer the activity. And afterwards, when I say time is up, you will raise your answer. Is that clear? Okay, guys, you will now start your activity. Okay, time is up, students. Now, exchange your papers with the other groups and we'll be going to answer the activity. Okay, everybody, please read the question number 1. So, what is the answer of question number 1? Very good. It is natural numbers. Then how about question number 2? Everybody, please read. Okay, it is a successor. Then how about question number 3? Everybody, please read, students. So what is the answer? Very good. It is axiom. Then how about question number 4? Everybody, please read. Okay, it is an inductive set. Then, the last one, number 5, everybody please read. So, what is the answer? Okay, guys, you got it. The answer is a theorem. So, I think everybody is perfect, am I right? Good job, students, very good. So, okay. Now, all of the words that part of our activity will be also part of our discussion for today. Our topic for today is all about Peanos axiom and recursion theorem. But before we continue, let me introduce first our learning objectives. At the end of the discussion, the students will be able to A. Discuss the Peanos axiom and recursion theorem, B. Differentiate the 5 Peanos axiom, and C. Perform group activity by applying the 5 Peanos axiom. Okay, now let's discuss the Peanos axiom. So what is Peanos axiom? Peanos axiom in mathematical logic, it is also known as Dedekind Peanos axiom or Peano postulates since it is based on the axioms of the German mathematician Richard Dedekind and Italian mathematician Giuseppe Peano, who introduced the 5 axioms in 1886. The Peanos axioms are meant to provide a rigorous foundations of the natural number 0, 1, 2, 3, and infinity used in arithmetic, number theory, and set theory. These are the 5 Peanos axioms. So axiom 1, 0 is an element of n, meaning 0 is a natural number. So axiom 1 includes one element into the natural number, which is the 0. So it is actually a very good starting point to actually define the entire system of the natural numbers. Now moving on to the next axiom or the second axiom, everybody please read. Okay, thank you. So according to second axiom, if x is an element of n, then the successor of x is also an element of n. Or in other words, every natural number has a unique successor in natural number. So we already know that in axiom 1, 0 is a natural number. And in axiom 2, if x is a natural number, then the successor of x is also a natural number. So combining axiom 1 and 2, if x is equals to 0, then it automatically implies that the successor of 0 is also a natural number. These two axioms doesn't enough to define what is natural number. Why? It is because it doesn't prevent if we say the successor of 3 is 0. That's why we need another axiom. Okay, now let's continue to axiom number 3. So according to axiom number 3, for every natural number x is an element of n, then s of x equals 0 is false. Meaning, or in short, 0 is not a successor of any natural number, or it is very impossible that 0 will be the successor of any natural number. So how to prove that 0 is not a successor of 3? So assuming that 3 is equals to 0, this implies that the successor of 2 is also a 0. We know that in axiom 3, 0 is not a successor of any natural number. That's why 2 is equals to 0 or 0 as a successor of 2 contradicts the axiom number 3. Therefore, 3 is not equal to 0. So, with these 3 axioms, do you think it is enough to define what is natural numbers? Or it is enough to compute our system of natural numbers? Okay, very good. Yes, that's correct. Because these 3 axioms doesn't prevent if we say 3 is equals to 2. We know that 3 is equals to 2 satisfies axiom 1, axiom 2, and axiom 3. Therefore, we need another axiom.
So for axiom 4, for all x, y is an element of natural number. If the successor of x is equal to successor of y, then x is equal to y. This axiom prevent 3 equals 2. To prove that 3 is not equal to 2, assuming that 3 is equal to 2 implies that the successor of 2 the successor 2 is equal to 1, then 2 equals 1. If we keep using the fourth axiom as a procedure, so 2 equals 1 implies that 1 equals 0. That implies to 0 equals 0. We know that in the third axiom, 0 is not a successor of any natural numbers. That's why 0, 0 is contradict the third axiom. Therefore, it must be 3 is not equal to 2. So, but it is not enough to prove that. So, we need to prove furthermore. So for the last axiom is axiom 5. If if B is an inductive set, then natural number is a subset of inductive set. If a set contains 0 and the successor of every number is in the set, then the set contains the natural numbers. A set B is called inductive if the following two conditions are satisfied. 1. Is 0 is an element of inductive set, and 2. If X is an element of inductive set, then the successor of X is an element of inductive set. For recursion theorem, the recursion theorem, also known as the fixed point theorem, is a fundamental concept in mathematics and computer science. It states that for any computable function, there exists a corresponding program that can compute it. In simpler terms, the recursion theorem explains how we can define functions that refer to themselves with their own definition. So this concept is particularly useful in programming languages and mathematical proofs. The recursion theorem has wide-ranging applications, from algorithms and data structures to formal logic and set theory. It provides powerful tool to problem solving and has greatly influenced the development of computer. So that would be for the recursion theorem. So any questions, clarifications, or violent reactions? So we will be having another activity. So this activity is true or false. Identify if the given example of each Peanos axiom is true or false. If the given example is satisfies the axiom itself, and false if it is not satisfied, write your answer on the provided manila paper and choose one representative to explain your answer. You will be given only 5 minutes to finish the activity. Afterwards, the first presenters will start to present their output. So we will be using also the same group from our previous activity. So for group 1, this will be your task. So you just have gonna state if is it true or not, then provide the answer if is it false. So for group 2, this would be your task, and also for group 3. So take time to answer. Then this would be your criteria for judging. So correctness, 5 is all answers are correct, and 4, 2 of the answers are not correct, and 3 if 3 of the answers are not correct. So for presentation, the presenters are explain the task clearly and organized. And 4, the presenters are explained that with few lapses and less organized. And for 3 points, the presenters are not prepared and explain the task with many lapses and unorganized. So criteria for cooperation, 5 points if all members are actively participated, 4 points if one of the members are not actively participated, and for 3 points, 2 or more of the members are not participated. So for time frame, 5 if submitted on before time, and 4 submitted after 1 minute of the allotted time, and 3 submitted 2 minutes after the allotted time. So your time starts now. So that would be great. So you deliver your all activities Good. So that would be, so we will be having for our evaluation. So for our evaluation direction, choose the letter of the best answers. Write your answer in a 1/4 sheet of paper as much as possible. Avoid any alliterations. So per 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 slide, we will be having a 2 minutes. So you can start now. So for number 1, which of the following is not one of Peanos' axiom? Letter A, 0 is a natural number. B, every natural number has a successor. C, 0 is not a natural number. And D, for every natural number is successor. So I'll repeat the choices. Letter A, 0 is not a natural number. B, every natural number has a successor. C, 0 is not a natural number. And D, for every natural number is successor is unique. Letter number 2, according to Peanos' axioms, what is the successor of 0? Letter A, -1. Letter B, 0. Letter C, 1. And D, none of the above. So, I repeat the question. According to Peanos' axiom, what is the successor of 0? Letter A, -1. Letter B, 0. Letter C, 1. D, none of the above. So for number 3, what is the successor function in Peanos' axiom? A function, letter A, a function that adds 1 to a natural number. Letter B, a function that subtracts 1 from a natural number. Letter C, a function that multiplies a natural number by 2. And letter D, none of the above. So for number 4, which axioms ensure that there is no natural number whose successor is 0? Letter A, 1, axiom 1. Letter B, axiom 2. Letter C, axiom 3. And letter D, axiom 4. So for number 5, according to Peanos' axiom, what is the successor of what is the successor of the successor of 0? A, 2. B, 3. A, C, 4. And letter D, successor is not defined for 0. So I repeat, according to Peanos' axiom, what is the successor of the successor of 0? Letter A, 2. Letter B, 3. Letter C, 4. And letter D, successor is not defined for 0. So for number 6, which of the following is axiom 4? Letter A, for all x, y is an element of natural numbers. If successor of x is equals to successor of y, then x equal to y. Letter B, for every natural number, x is an element of natural number. So successor x is not equal to 0 is false. Letter C, if the V is an inductive set, then natural number is a subset of inductive set. Letter D, if X is an element of N, then the successor is an element of N. Number 7, which of the following is axiom 2? For all X, letter A, for all X and Y is an element of natural numbers. If successor is an element is equal to successor y, then x is equal to y. Letter B, for every natural number, x is an element of natural number, so the successor is equal to 0 is false. Letter C, if V is an inductive set, then the natural number is subset of inductive set. Letter D, if X is an element of N, then the subset of X is an element of natural numbers. So for number 8 and 9, which axiom allows us to perform mathematical induction? Letter A, axiom 2. Letter B, axiom 3. Letter C, axiom 4. Letter D, axiom 5. Number 9. Which axiom ensures that every natural number has a unique successor? Letter A, axiom 2. Letter B, axiom 3. Letter C, axiom 4. Letter D, axiom 5. So for the last number, this theorem, also known as the fixed point theorem, a fundamental concepts in mathematics and computer science. Letter A, Peanos theorem. Letter B, Peanos axiom. Letter C, recursion. Letter D, recursion theorem. So that would be all. So are you done? So pass your paper forward. So for your assignment, advanced study about the transitive sets. So I will allow you to search what is inductive set, but you have to study what you have gathered about the transitive sets. So that would be all. Thank you.